Okay, hello friends, I'm Ashish Tabari, founder and CEO of Aximize, and let's talk about coverage-driven formal verification for RISC-V ISA compliance. So as some of you may know, we built this cool formal ISA app this summer, which can be used to visualize ISA and obtain a lot of interesting coverage analysis around ISA. So I'm going to be talking about why you should trust this app, because we've invested in coverage analysis and building this exhaustive coverage model. So we've got about 27,000 properties, including assertions, covers, and assumes, and we've used this app to now build end-to-end proofs for multiple processors to prove that they comply with the RISC-V ISA without any cut pointing and black boxing. And you can run this with any formal tool you like, no vendor lock-in, and it catches bugs, both in design specifications, occasionally in our own code, and a coverage model will provide evidence and confidence in the overall verification. So as I said, it has found numerous bugs in different processors and has been used to formally verify processors. Now, there are challenges with property checking. This is why we built this app, especially with formal property checking. So finding that bugs are true bugs and not spurious test bench issues, avoiding true design bugs, building exhaustive proofs of bug absence, establishing when you have an inconclusive proof, is there a bug beyond a bound? These are all very hard questions for anybody who's doing formal verification. So we need a coverage model for sign-off to increase confidence in our ability to say we have done a good job. But which coverage model? Each formal vendor will tell you what they have is complete. And without coverage, we can never know if we are done. So what we've done is we've built a well-rounded coverage model encompassing different aspects of coverage, which we're going to talk about in this talk. And all of this is vendor independent. There is one aspect which is vendor dependent, but you still have the possibility of running that aspect with different vendors. So what can go wrong? Well, many things can go wrong. There are many actors in here. There are about 7 of these actors, and each one of them can cause a problem. You could have bugs in the ISA itself, or in the sale model, or in the microarchitecture spec, or in the design, which you already expect to have, or in our test bench, or in the formal verification tool itself. We got to reconcile all of this information before we can say something is a bug or isn't. And one way we do this is file tickets on GitHub, talk to the designers, understand if it's a model problem on our end, or it's a design problem or a specification problem. For example, we found an inconsistency in the RISC-V ISA in the 2017 version, where it said on one of the pages that you need to raise an illegal instruction exception if the immediate fifth bit is not 0. But it turns out that on page 104, if you're decoding these 3 instructions, bit 25th can never be anything other than 0. I ended up encountering this issue as part of CVE4 verification, and an interesting conversation between me and the designers recorded at this Git ticket, which you're welcome to go and read. But what I'm trying to say is we can have problems anywhere. So coverage goals, what are we trying to establish here is that anything we verify with our app on a RISC-V processor is sound and complete. So to start with, do we have a list of all necessary assertions and covers, processor coverage targets? Do we have proofs that assertions are actually doing the right job? So, establishing absence of bugs. What percentage of design code is covered by our properties? Are our properties proving anything sensible, or are they just properties that prove trivial properties? Do we have checker completeness? For any given check, is it checking what it needs to check in its entirety? Are constraints blocking relevant stimuli? Okay, constraints can block relevant stimuli in formal, although we may not need to inject any explicit stimulus in formal as compared to simulation. And then, are all interesting functional scenarios covered? What about the interaction of this instruction with that instruction, with the interrupt, with debugs, with stalls? What about accesses to CSR? So we have this heat map view of this to say some of these activities are easy, but some of them can be really hard. And the real hard bits are actually the ones where we have tried to build automation in our app to make it easier for the end user to obtain that level of confidence. And we're going to talk about it today. So processor coverage targets are derived from requirements, which are themselves derived from a verification plan. For example, this is the one for CVE4, which then transforms into a number of different properties. In case of CVE4, we are running 27,000 properties. And do we have enough checks? We believe, yes, we have. We are following the specifications, we are following the changes in the microarchitecture specification, and we are constantly updating our app to actually adapt to what the requirements are for different processors. For example, if you look at the description of what exceptions should be raised, how they should be handled in the processor, the privileged ISA describes an MCOS register to be updated, for example, under different conditions with interrupts, without interrupts. What exception codes are written? Are they written for the right reasons or for the wrong reasons? Is the correct exception code generated for the correct reason? You know, for example, if it's an illegal instruction, we should be writing 2. If it's a breakpoint, we should be writing 3. If you raise a load address misaligned exception, we write 4. If you're not raising a misaligned address exception for load, you shouldn't be writing anything. So for example, in CVE4, we proved that we can never generate such an exception. The processor can never generate such an exception. For jump and link instructions, for example, we have 17 properties to establish different cases. Some is specific to the CVE4 processor, for example. So overall, 300 properties today checking exceptions. Other things we've looked at is, can we get stuck in states, illegal instruction behavior, register coverage, proving that every instruction can decode any register between 0 and 31, but no more. If the design was ever instrumented for Trojan insertion, these assertions would fire. All CSR registers are being correctly decoded. The ones that have to be written are written. The ones that have to be only read are not written. If they are written, then we must raise an exception. If the code is raising an exception, we check it does. So you see, you get how we are actually building this model very much depends on what the specification requires us. I side and D side, you know, are we generating enough instruction addresses on both sides and data addresses? All branches of decoder are exercised correctly. You know, can we inject unlimited number of stalls, or have we built a formal verification environment where I block the stall, right? Is the environment loose enough to allow all kinds of interactions, interrupts, exceptions, their interplay? All of the stuff is derived to build our coverage model. Accession coverage is probably the easiest. Just look at the outcome of pass and fail. So for IBEX and zero RISC-V, 50% results in less than 30 minutes, 80% done in 2 hours. What is happening? Let's take a look at an example of BEQ, branch if equal to. This is an instruction in ISA that says you branch if the RS1 and RS2 registers are equal. We have 6 assertions and we have a number of cover targets that we've pre-compiled and come out of the app. One of them, for example, back-to-back BEQs, we can't have them. Why can't we have them? We can't have them because one cycle after a conditional branch is decoded and sent for execution, the decode and execute is blocked. In fact, we were able to prove this assertion here right now that it is blocked. In fact, it is blocked for not just one cycle, but the second cycle too. But in the third cycle, it isn't blocked, and therefore we see that this assertion has failed, showing that actually the pipeline is working as intended. So our coverage model allows us another dimension of analysis, which allows us to conclude that our test benches are not overly constrained, they're doing the right things, they're aligned with the design. This is really, really exciting stuff. Property-driven design coverage, for example, this is a snapshot from Cadence Jasper Gold, which actually shows that if we were to exercise code coverage analysis on the whole core in the presence of our test bench, 88% of the design is reachable. The ones that are not reachable are marked in red, and the ones that are dead code are marked in black. A lot of the dead code is coming out of FPU being disabled. Our own test bench has got 99.36% reachability. In terms of what aspect of the design is covered by our checkers, the asserts on BEQ, 76.51% of the entire core is covered by our BEQ instruction check. This is awesome because, you know, that shows like we are covering 76% of the sleep unit, 81% of the fetcher, 79% of the ID stage, 81% of the execute stage. And you can go through these, you can expand these entries and examine these results and understand what is happening for the right reason and what isn't. But overall, this formal coverage is then giving you feedback to know how good or bad your test bench is. So this process is repeated for all of the instructions. So what else? So Can we inject potentially infinite number of stalls? We wrote a cover property to say, okay, can we send 500 stalls between any two instructions? And the formal tool says, yes, you can. You can have a store half word here and have nothing in it until 500 cycles have elapsed, and you can have an add-I instruction. So, we're just trying to show you that in our formal test bench environment, we're not blocking the number of stalls to any finite number. We do rule out bad constraints. We have a number of different techniques. So for example, lifting unnecessary assumed properties, finding bad configurations, detecting over constraints, finding bad constraints in the properties in our SVA, establishing that the mapping points are correct. If you have a different mapping point to what a designer thinks we should, we prove that they're equivalent. So we do all of this. So for example, when we actually reviewed the configurations, we found that opcodes marked as custom 0 and custom 1 are in use by CVE for when pulp extensions are enabled. We reported this to the designer. Designer asked us to check what if there's configuration when X pulp is 0, what happens? And we said, well, these same properties are proven. So it turned out that what we were raising was already something that was under discussion. So you can follow the chatter on this ticket. But what I'm trying to say is just playing with configurations alone highlights interesting RTL issues and so on. So ruling out that there are no design or test bench issues. So here is another example of what we did when we lifted the constraint on the memory side, data memory side, and we prevented the memory to return the valids on a store. What happened? So we were writing an ISA check for eBreak scenario 1 for CVE4. And we said if you have an eBreak instruction between 0 to 3 cycles later, in fact, it's on the third cycle, the mcosq register gets updated. What happens is this property failed. And what we actually noticed was that if the eBreak had happened a cycle after the store instruction, then basically you can't update this. And the reason is because the store instruction is expecting a data rvalid_i to come back. The memory isn't returning anything because we just lifted the constraint, and it is blocking a privileged instruction like an eBreak. We thought it's a genuine issue, but designer also has a point in that this is an issue raised on the memory side. Our point of view was that because eBreak is triggered from debuggers, it should have higher priority and it should be able to kill the store instruction. But what I'm trying to say is that these issues identify very interesting artifacts. In fact, after we wrote this property and started to see this behavior, we went about analyzing it in great detail. Is my check catching the bug? So design mutations. So one of the persons asked us, what happens if you actually have a bug where you trigger a BQ instruction in this cycle and the update needs to happen in this cycle, but in the intervening cycle, if the next state of the program counter was corrupted, can your BQ check catch this bug? The answer is yes, we can. So for example, we did insert this bug where we randomly mutated the design and all of the properties related to BQ failed. In fact, we have an invariant on the program counter which says what are the legal states of the program counter. That failed as well. So this process has been done to check the robustness of our checkers to see what kind of known bugs they can catch. But is this enough, proving that I believe it isn't, because how do we know that all instruction sequence interleavings have been verified? Just because I tell you we have proven doesn't make it right. Show me that you've tested all sequences. Prove it that you've tested all sequences. So what we're saying here is, guys, let's do scenario coverage. Have we covered all interesting scenarios? What is scenario coverage? Proving that specific instruction sequencing works and visualizing it. So for example, conventional verification relies heavily on architectural testing. And if you were testing assembly programs like this, you're going to be checking specific traces, right? Specific sequences. But how about verifying that certain optimizations do not break the functionality? For example, is forwarding working correctly if you're sharing registers between consecutive instructions? So a lot of fine behavior about subtle behavior that can emerge from optimizations in the core. And can it destroy the interplay of different instructions? So that's what we are looking at when we talk about scenario coverage. So, similar to simulation-based functional coverage, in our case, we prove as well as cover. So for example, 4 cycles after reset has been detected, we send a subtraction instruction 2 times, consecutively or non-consecutively. A cycle later from that, we send an OR instruction in the pipeline, and a cycle later from that, we issue an AND instruction once. And this entry is specified in a spreadsheet, and what happens as a consequence of this, we prove whether or not the OR instruction works correctly when sub is a prefix and AND is a suffix, and then we are able to generate a trace looking like this, which shows all of the dependencies that the tool has automatically obtained. And the good thing is you can get all of this for free. All you have to do is to write an entry like this in a spreadsheet, and you can see visualizations coming out and proofs coming out. So for example, we have proven properties on OR instruction, for example, that it always works correctly. But if you wanted to see if the scenario coverage is there, we'll generate all of these properties, and we will actually tell you that this is or isn't the case. So how many scenarios to analyze for a processor, 4-stage pipeline like CVE4? We can write a specification in this format. So for example, we just populated an Excel spreadsheet, and we wrote different behaviors of like store byte, store word, misaligned, aligned, and then you have a sub instruction followed by a shift right arithmetic, kind of considered a large number of permutations, but not exhaustive, because the number of permutations is a huge number. Even if you understand 40 user instructions, we're talking about several thousand combinations. But even on a 84-row spreadsheet, we're able to generate like 746 properties that exhaustively proved a lot of the behavior specified in the spreadsheet. And this is actually very cheap. It took us a couple of hours to get this kind of result. And depending on how you partition these proofs, you can make them even more efficient. So coverage-based solution, we've talked about this being related to processor coverage targets coming from requirements, assertion coverage, property-driven design coverage that we talked about using tools, understanding completeness, doing the things that we have talked about, for example, relaxing constraints and breaking designs to understand how robust the design is. All good stuff, hard but necessary. We've done it, so we know that this stuff is sound. You can take our properties and put it on your processors and see the results. Scenario coverage is this new development we did this year, and I talked about this. Now, what does it do for us for coverage? So for example, what I believe is that there is a combination of qualitative and metrics going on in here. So processor coverage targets, you can look at it, understand what's the quality of your targets. Assertion coverage will give you a count of pass and fail. This is a little bit qualitative. We know or don't know, but to a subjective level where a checker is complete or not. There's not necessarily a way right now to obtain a metric. Same with OR constraint. Both are very important though. But property-driven design coverage will get you metrics. So for example, it gives you the code coverage on the entire design. It gives you a checker-dependent analysis. You could also run mutation analysis. And all of this is pretty automated. And lastly, the scenario coverage. So you've got to actually include all of these different aspects, 6 different aspects in your verification environment. If you're doing formal verification, for example, we would like to understand the quality of our verification in a more holistic way. So if we have done all of this, we believe we've got a very good environment for verification. So we've built the industry's first and only end-to-end vendor-neutral formal verification solution for RISC-V that verifies ISA compliance for user and privileged instructions. Our solution has been tested with multiple tools and for different processors. So you can verify beyond doubt with formal ISA because we give you bugs, we give you proofs, and we give you this extra information coming from coverage, which will give you the confidence to sign off your designs. So now I'm very happy to stop at this point and take any questions. Thank you very much all for coming today. And if I cannot answer your questions today, feel free to write me an email at ashish.dabari@aximize.com and I'll be happy to get back to you. Thank you very much.